Hi, I'm Noah. I guess I introduced myself already. This is going to be joint work with Sasha Golovnev and Huck Bennett. We were all at NYU at the time of this work, but Huck's now at Northwestern and Sasha's at Yahoo Research. Someone told me last time I gave this talk, which was like a week ago, that I should call this fixed parameter or fine-grained hardness of CVP. So maybe that's how you should interpret this title, but it's too late to change the title of the paper. And before I talk about CVP, I just wanted to sort of mention, I don't know if you guys know this, but the spacecraft Cassini just crashed into Saturn, and it's really cool. This is probably way more interesting than my talk. Saturn has a giant hexagon on top of it, which Cassini discovered. Saturn has giant storms in it, lots of cool stuff. This is a picture from the moon Titan of Saturn from Cassini's Huygens probes. Anyway, lots of cool stuff about Cassini. You should look this up yourself. And this just crashed into Saturn's atmosphere, and it's weird.
That's a simulated one.
This one's fake. Everything else is real. Yeah, because we don't have another spacecraft to take a picture of Cassini crashing into. Yeah, we only have one. Yeah. So, closest vector problem. So the closest vector problem is a problem about lattices. I'll introduce a lattice. It's a discrete set of vectors in d-dimensional space. So here's what it looks like in 2 dimensions. It's the highest dimensional draw for you. It's specified by a basis, b1 through bn, of linearly independent vectors. So here's the basis of this lattice. And the lattice itself is the set of integer linear combinations of the basis vectors. So like this guy over here is b1 plus b2, this guy is 2b1 plus b2, etc. So all of these guys have integer coordinates when they're expressed in this basis. And just some vocabulary, n is going to be the rank of the lattice, and d is the ambient dimension. The closest vector problem takes as input some target vector t and a lattice, and it asks us to compute the distance between t and the lattice. So by distance between a set and a point, I mean the minimal distance between an element in the set and the point. And what do I mean by distance? Here I mean the LP norm. So this is the definition of the LP norm. So for example, you might know this norm when p equals 2, which is our favorite norm because we live in it. But for other p's, it's a fun norm too. And so as I said, CVP is the computational problem that asks us to compute this distance. So just to be concrete about it, the input is a basis and a target vector t, and the output is the minimal distance between a guy whose coordinates are integral in this basis and t. And when you draw it like that, the problem looks rather easy, but it's not so easy. Sort of a picture like this may be more evocative, right? So you're just given the basis and the target t, and you want to know whether or not there's a close vector to this. It turns out that in this case there was. I don't know if anyone saw that. I had 2 dimensions, it's easy, but maybe not for us, for computers. So if you've never seen this problem before, it has quite a number of examples, or more generally, computational problems on these geometric objects, on lattices, have many applications. In particular, they're related to decoding linear codes, to factoring polynomials over the rationals, to integer programming. They've been used for cryptanalysis, and more recently, we're really interested in these things because they're used for lattice-based cryptography. So that's sort of the hot application right now, and I'll say a little bit more about it, but still just buzzwords. Lattice-based cryptography is really cool because we have public key cryptography that seems to be secure against a quantum computer, as far as we know. This is not true of like what we use now typically, which is like RSA, which is based on factoring, or stuff based on discrete log, because both of those are known to be broken by quantum computers. You can build really cool primitives with a lattice-based crypto, like fully homomorphic encryption, due to Gentry. And these things have these worst case hardness proofs where we know that they're as hard as worst case problems as opposed to average case problems. And perhaps most importantly for this talk, these things are about to be used by a lot of real people, like on the scale of the internet. And as evidence of this, I present first this announcement by NIST. So NIST is the National Institute of Standards and Technology. They sort of decide what crypto gets used in practice. And they've asked for a submission for post-quantum cryptography, by which they mean lattice cryptography. The due date's November 30th, 2017. And Google actually like a year ago now, Google did a large-scale test of lattice-based crypto in which they embedded it in like a beta version of Chrome, and yeah. So these things have been tested at extremely large.
What?
They embedded it in like a beta version or something of Chrome, so that people could use it. I don't know the exact details.
Lattice-based.
Yeah, lattice-based. Yeah, like this LWE-based key agreement. Yeah, and so there are lots of proposals out now with fun names like Frodo and New Hope and things like that. But the point is, these things are going to be used. So we should know some stuff about lattice problems before we use these things, hopefully. So we know that there are some algorithms, so there are some fast algorithms for solving these. They're relatively fast. In the L2 norm, which is our favorite norm, we understand CVP fairly well. There's a 2 to the n time algorithm, which is joint work with Agrawal and Dadouche. In the LP norms, they're much worse studied. There are n to the order n are algorithms that solve it exactly, and there are 2 to the order n algorithms that find maybe not the exact distance, but up to a constant factor approximation will find the distance. And we have hardness results as well. We've known hardness of CVP for a while, since '81 due to Van Emde-Boas. We've known that it's NP hard, and there's been a series of work showing that it's hard to approximate. But we don't know so these hardness proofs are pretty good if all you want to know is whether or not there's a polynomial time algorithm. But what we don't know is what the right complexity is exactly, what the fine-grained or quantitative complexity is, right? So as far as we know, based on these results, nobody will be surprised if there's a 2 to the root n time algorithm for CVP. And even like a 2 to the n over 20 time algorithm would break all crypto in practice. So from my perspective, this is kind of scary. Because if we're going to use this stuff on the scale of the internet, we should probably have some reason to believe that this isn't the case.
So, I mean, there are 2 to the n to the 1/3 algorithms for factoring.
Yeah, this is true, and we therefore choose our keys to be large enough to deal with that, right? The keys that people choose for lattices.
That was on point, so I wasn't sure what you said was great.
Oh, it would break everything we do in practice because everything we do in practice assumes that those algorithms don't exist for CVP.
Oh, they are assuming that kind of strong hardness?
Well, they assume specific hardness of related problems. Yeah.
But that kind of one.
Yeah. Yeah, right? I mean, you know, like they can't just say there's no polynomial time algorithm. They have to say there's no algorithm that'll run in 2 to the 128 time or whatever.
You just get larger keys.
Yeah, but ask an engineer to do that. And so like, actually the big game in lattice-based crypto has been reducing the key size as much as possible while still arguing that you're secure. Because if you want this stuff to run internet scale, people get very, very concerned about, you know, even a factor of 2 or whatever.
So wouldn't you need some kind of a average case version of this for cryptographic application?
Okay, so CVP isn't exactly the right problem. Exactly the right problem would be approximate SVP and like an average case approximate SVP or approximate bound distance decoding, something like that. But CVP is harder than these problems, so we should at least show that it's hard. And in practice, we solve all of these problems more or less the same way. We solve the approximate problems by reducing them to the exact problems, and then we solve the exact problems with the only algorithm that we know. Yeah. So everyone understand the situation? Cool. How do we prove quantitative hardness of something? So for example, how could we prove that there's no 2 to the 0.99 n time algorithm for CVP? This would be nice. It would rule out the 2 bad cases I showed in the previous slide. So how does one do such things? Obviously, we can't prove lower bounds unconditionally, or almost never can. So we're going to need some kind of conjecture. The conjecture that we'll use is the Strong Exponential Time Hypothesis. So this is a conjecture based on KSAT. So KSAT is, takes as input a formula that looks like this. It's the end of a bunch of ors. So you've probably seen 3SAT, in which the number of ors is 3. And the number of guys in each clause, these are called clauses, is 3. And more generally, there's the problem KSAT, in which the number of literals per clause is k. And just some vocabulary, we'll call the number of variables n and the number of clauses m. And the conjecture, known as SETH, due to Impagliazzo and Pittori, is that there exists a constant integer k, so for sufficiently large k, no algorithm can solve k-sat in time 2 to the 0.99n. Right, so we need to be careful about these conjectures. One might want to conjecture that there's no 2 to the n time algorithm, faster than 2 to the n time algorithm for 3-sat, but that would be false. So we need a more careful conjecture. So this is what we need. It's fairly well studied. Some people believe it, some people don't. But if we want to show that CVP doesn't have a fast algorithm, assuming SETH is true, then we need to show a reduction from k-sat to CVP, but we have to be very careful about the parameters. We want n variables in the k-sat instance to correspond to a lattice of rank n in the CVP instance. So normally we'd be happy with a polynomial relationship here, but for such fine-grained results, we really care about. We wouldn't even be happy with order n here. We want exactly n. Does that make sense? Okay, so this is going to be our goal, and I will show you the reduction. So let's first consider a 2-sat, which is a very special case of k-sat. In particular, you might know that 2-sat has a fast algorithm. So reducing 2-sat to CVP is kind of trivial, or is trivial, but let's do it anyway because it will be instructive, and for a larger k, the problem's hard, right? So we want a reduction that works for all k. I'll give you a reduction that works for k equals 2. So here's what we're dealing with. We're dealing with some 2-sat instance that looks like this. And we're going to build, so we want a CVP instance, so we're going to build a basis. And it's going to look like this. So it's going to have a sort of top part, phi, which is going to depend on this instance in some way. And it's going to have a bottom part that's just always the same. It's just always some large scaling of the identity matrix. These 2's are just for convenience. And we need a target as well. And the target, again, is going to have some top part, which I'll show you guys later. And the bottom part is just going to be a bunch of alphas. So this scaling these alphas. And so before I tell you the interesting part, let me just explain why there's this identity matrix here and these alphas there. This is a sort of a standard gadget when you want to show hardness of CVP. So let's call this vector bold alpha. And let's just look at how sort of the contribution of the distance just from these coordinates behaves. In particular, if we take a vector whose coordinates are in 0, 1 to the n, then this identity matrix, all the values in these coordinates are going to be either 0 or 2 alpha. So the distance contribution in each coordinate will be alpha. So the total distance raised to the pth power, because that makes it easier, will be alpha to the p times n. There are n of these guys, each one contributes alpha to the p. Make sense? Nothing up my sleeve? If on the other hand, one of the coordinates is not 0 or 1, then we'll get a larger contribution. It works out to be exactly this, but the point is we get some larger contribution. So we're going to take alpha to be gigantic, and then for our purposes, we won't care about any lattice vectors with coordinates other than 0, 1 to the n. So this is nice because we're going to want z to correspond to an assignment to variables, and we don't want to assign to our sat instance a variable with value 2, because that doesn't make sense. So we only want 0 or 1. So we can assume that z is in 0, 1, and now we can just sort of forget about it, and let's talk about this more interesting matrix phi. Okay, so remember phi's on top here, so let's talk about that. So phi is sort of the most obvious matrix you could imagine coming up with. So it's n by m, so it has n rows, n columns, we want rank n, and m rows, which is the number of clauses, and we just put a 1 in phi in the ij spot if xj is in clause I. We put a -1 if not xj is in clause I, and we put a 0 otherwise. And we assume that, xj and not xj never appear together, because that would be silly. So, I mean, this is the dumbest reduction one could imagine, I think. But if we assume that z is in 0, 1 to the n, then what we get here when we look at sort of the ith coordinate of this guy, multiplied by z, we get the number of positive literals that are satisfied minus the number of negated literals that are not satisfied. Does that check out? Right? So everywhere I have a 1 for a positive guy, I'll get a 1 here. Everywhere I have a 1 for a negative guy, I'll get a -1 here. So this is nice because it's sort of monotonic in satisfiability or something like that. And then if we set our TI to be 3 minus twice the number of negated literals in the clause, then with sufficient amount of staring, you can see that the ith coordinate of the difference here will be twice the number of satisfied literals minus 3. In other words, the absolute value of this difference will be 1 if the ith clause is satisfied, 3 otherwise. So I'm just going to sort of shut up for a second and let you guys stare at this to make sure everyone sees. There's nothing complicated going on here.
The ambient dimension is n plus m.
The ambient dimension is n plus m, yeah.
Isn't it too much?
No, we don't care. It's going to get much bigger.
So what's the parameter?
The parameter is just the rank.
It's just the rank of the lattice. We
Yeah.
don't care if it's embedded in some.
No, we don't care about it. I mean, as long as it's polynomial or whatever. So if we combine this all together and we look at the total distance, again raised to the pth power because that makes it easier, each satisfied clause contributes 1, each unsatisfied clause contributes 3 to the p. So we can rearrange this a little bit and we can see that the distance is exactly 3 to the p times the number of clauses minus some smaller number times the number of satisfied clauses. So in particular, if we know that all the clauses are satisfiable, then the distance here will be m, are satisfied, then the distance here will be m. If they're not all satisfied, this value will be smaller than m. So the distance between t and the lattice tells us exactly the number of the maximal number of satisfied clauses. Yeah?
What happens if t is the infinity?
Oh, something else happens. Then it's just a max, yeah. Yeah. So if p equals infinity, then it's easier, although what I say here is not true. I should have written p less than infinity somewhere here. We handle the case p equals infinity separately. But it's actually easier. But something to notice is that actually the distance between t and the lattice here doesn't just tell us whether or not the instance is satisfiable. It tells us the maximal number of satisfiable clauses. And so actually I lied to you when I said that we're going to reduce from an easy problem. So we didn't just reduce from 2sat, we sort of accidentally reduced from max 2sat. Max 2sat, which is the problem of figuring out the maximal number of clauses that are satisfiable, is actually hard, whereas 2sat is not. So we actually picked up a little bit for free, and I guess Garfield's happy. And so this was a really dumb reduction, but let's stop and think about what we've proven, because actually we proved something non-trivial already. In particular, max 2sat is ETH hard. So for example, if we assume SETH, which we're willing to do, then we know that there's no 2 to the low of n time algorithm for max 2sat. So we want something stronger. We want, we care about the constants in the exponent, but this says that if we take something subconstant in the exponent, then we can rule it out. We can rule out subconstant in the exponent. We just can't tell you what constant there we should put. Does that make sense?
I see. So n here is just referring to the number of the dimensions.
It's the rank. The rank. It's
Right.
yeah.
Not the size of the entries.
Yeah, not the size of the entries.
So that's how you define it.
Yeah. So and this is the right parameterization. Yeah, I guess I should have made that clear. But this is the right parameterization. And in the L2 norm it doesn't matter, but in higher dimensional LP norms for other than p equals 2, there's a difference between the ambient dimension and the rank, right? So we've actually kind of proven something non-trivial already. We've proven that there's no 2 to the low of n time algorithm for CVP for any in any LP norm, assuming SETH or even just ETH. And this is not that impressive because this result was already known in folklore, and there's even unpublished work by Samuel Yom, an undergraduate student of Vinod Vaikuntanathan. But we can kind of do a little bit better if we're willing to make an absurd assumption. So in particular, the fastest algorithm for max 2sat runs in time about 2 to the 0.78 n. It's due to Ryan Williams and stood for about 12 years now. So if we make the kind of extreme assumption that this is optimal, then we get a really nice lower bound for CVP. We get 2 to the 0.78 n. And remember, we had this 2 to the n time algorithm in the L2 norm. So this is like pretty close to tight. Yeah. But of course, this is a really extreme assumption. In fact, I gave this talk in front of Ryan Williams, and he laughed when I said this, which is fair. So this is not a very safe assumption, so we're gonna try to do something better. But I still want to note that like we've already gotten something non-trivial out of this really dumb simple reduction. So how do we generalize this to k-sat for larger k? So remember in the 2-sat case, we had this really nice formula where we had that the ith coordinate of this difference was exactly twice the number of satisfied literals minus 3. And we implicitly use the fact that a 2-sat clause is satisfied if and only if the number of satisfied literals is 1 or 2. Therefore, this absolute value is 1 if and only if the clause is satisfied. And this is because 2 and 4 are equidistant from 3. And this is such an important fact that I'll provide a proof by picture. It's really true. In the 3-sat case, this is no longer true, right? So a 3-sat clause is satisfied if and only if the number of satisfied literals is 1, 2, or 3. And so if we try the same construction with 3-sat, we'll fail. And this is because we can't find 3 distinct numbers that are equidistant from some other number, right? The number line just doesn't have space for that. So we really get stuck here. And our solution is to increase the dimension, right? So we can't find many distinct numbers that are equidistant from some other number, but we can find many distinct vectors that are equidistant from some other vector. So what we're going to do is we're just going to look at our reduction, and we're going to, everywhere we see scalars, we're going to replace them by vectors. So before we had phi ij was 1 or minus 1, depending on whether xj was positive or negative, or 0 otherwise. So no more scalars, let's make them vectors. So now phi ij, abuse of notation, so phi ij is now a vector. And we're going to make it positive vector, negative vector, depending on whether it's positive or negative, and 0 if it's not in the clause. But you see now I have to have this index. So I can't use the same vector everywhere. If I just use the same vector for everything, then everything's going to live along a line, and there will be no difference between the scalar case and this case. So I have to use different vectors. So I want each clause to have a bunch of different vectors corresponding to it. And so the way I do that is I just say the lth literal in the clause is going to get VL. So the first guy that appears in the clause will have one vector. The next guy will have another vector, etc. Does that make sense? At least notationally or whatever? Okay. So now I'm going to replace ti, which was just this nice scalar, 3 minus twice the number of negated literals, by a vector. Now it's going to be t star, where t star is going to be something I'll show you later, minus the sum over all negated literals of the corresponding vectors. Yes?
So it depends just on the position in the clause. It's nothing.
Yeah.
The name of the variable.
Yeah. There's nothing important about L. Like as long as I choose L distinctly for each element in the clause, it's fine. Yeah. So just a natural way to choose it. Yeah. So again, this is just I don't want them to be on a line. I really want distinct vectors. And if we stare at this, we see that the sort of ith coordinate here, which is now a vector, for an assignment 0, 1, z and 0, 1 to the n, is going to be the sum over the satisfied literals of the vector corresponding to that literal minus t star. So again, this requires a small amount of staring, but it's true. Maybe it's actually easier to see than in the other case. So let's just ask what we need this formula, these VLs to satisfy to make this a good reduction. So we have this property, and what we really want is we want satisfied clauses to always contribute the same amount, and we want unsatisfied clauses to always contribute more than that. So it's important that satisfied clauses always contribute the same amount, because let's say that a clause satisfied once is worth less than a clause with 2 satisfied variables in it. Then maybe I could have some horrible k-sat instance in which a lot of clauses are satisfied twice, and one clause is not satisfied, and maybe my reduction would recognize that as a satisfiable instance, right? So it's really important not just that this distance be smaller when this is satisfied versus unsatisfied. It's important that they all have the same length. So we want this vector to be constant and smaller than the norm of t star whenever the sum is non-empty. So when the sum is non-empty, we have a satisfied clause. We want this to be some constant. And when the sum's empty, we just get the length of t star, and we want t star to be longer than that constant. We have a goal now. We want to find these vectors v1 through vk living in some dimension, say m, and some t star such that for all non-zero y's in 0, 1 to the k, vy minus t star is 1, but the length of t star is greater than 1. So this is this sort of weird geometric object. Let's see what it looks like. We call them isolating parallelepipeds. And the reason we call them that is because they look like this. So here's an example with k equals 2. They are in fact parallelepipeds, right? So v times y for y in 0, 1 to the k is exactly what a parallelepiped is, or parallelogram if you prefer. But in higher dimensions we like to use something that's very hard to pronounce. And we call it isolating because it has this property, right? So we want the distance from t star of all of these vectors to be constant, to be 1, and we want t star, we want 0 to be farther away. So we call it isolating because I think of 0, like all these guys have friends and this guy's lonely, he's isolated. So in 2 dimensions, or for k equals 2, these guys exist. Here's one in the L infinity norm. It's not hard to find them for any LP norm. And I think they're rather pretty interesting objects. We can ask, do these things even exist for large k? I'll just spoil things. I'll say most of the time they do. What do I mean by most of the time? Well, first of all, for odd integers, they exist for all k. And just plugging in what I gave you before shows that if SETH holds, then for all odd integers p, CVP is 2 to the 0.99n time hard. I sort of said very little, but I just got like a fairly big result, right? I recommend trying p equals 1 yourself. So just try to come up with an object that satisfies this with p equals 1. It's not very hard. For larger p, it's quite hard, or I think it's hard. But here's the letdown. For even integers, these things sort of don't exist, or they exist if and only if k is less than or equal to p. So this is really, really bad, because in particular, 2 is an even integer, and we like the L2 norm a lot. In particular, we only have a fast algorithm in the L2 norm, and usually we prefer talking about the L2 norm, right?
Fast as in like 2 to the n.
Yeah, as opposed to n to the n.
2 to the n log n probably exists more than 1.
Yeah. Yes. So 2 is an...
Keep shifting.
Well, okay. What I mean is an algorithm that approaches this. You know, I'd like a tight result. Yeah, maybe fast is unfair. So this is really depressing. I mean, you know, maybe the L4 norm's not that exciting, but the L2 norm really is. And of course, this is a really strong result. This is a really strong negative result in the sense that for p equals 2, it means we can't go larger than k equals 2. So I showed you k equals 2, and we can't do k equals 3 even. So that's depressing. And then we have this sort of harder to interpret result, which is that for any fixed k, these things exist for all but finitely many values of p. And one way I try to interpret this is that if I have a non-constant p, let's say p approaches some constant, but never touches it, then for sufficiently large n, this must exist. You see that? So if there are only finitely many values of p where this can exist, if I have p approaching some number, as it gets closer and closer and closer, eventually it will be closer to that number than any of these finitely many values, so it must exist. So particular plug in p naught equals 2 here, I can't give you exactly p equals 2, but I can give you, say, p equals 2 plus 2 to the minus n, or something like that. Yeah?
In the cryptographic applications, which norm are
So in the cryptographic applications, we usually talk about the L2 norm. I mean, for SIS, we really often define the problem in the L infinity norm. We still tend to solve it with the same L2 norm algorithms. I mean, they're typically for polynomial approximation factors, or they're always for polynomial approximation factors, where the norms are more or less equivalent.
So hardness result for the L2 norm will satisfy the cryptography. So for L2 plus 2 to the minus n norm will satisfy the cryptography.
Are there cryptographers in the audience? Who's satisfied? No, I mean, well, okay, so there are a lot of reasons why a cryptographer might not be that excited about this. I mean, one is that they don't care about the exact problem, they care about the approximate problem. The other is that they care really more about SVP than CVP. Yeah, and the other is that there really is a big difference. Yeah, so this is misleading. I mean, I like it because I want to use it as evidence that the L2 norm is hard, but things really change when you go from L2 plus 2 to the minus n to 2. There's a really big gap there. Like, you know, I don't know how to solve CVP for such a ridiculously close to L2 norm. Yeah.
So what about, is this all for integer p's or like, especially this except finitely many?
Wait, which?
So fractional p's.
Yeah, except finitely many, sorry, yeah, that means non-integer.
And
So all odd integers, not...
About 2.3.
Yeah, 2.3 almost certainly yes, although I can't tell you a specific.
Oh, but you don't have a result like for odd. So you don't know that.
Yeah, I don't know specifically 2.3, but I know that there's only finitely many exceptions. Maybe 2.3 is one of them.
So,
Yeah. Does everyone understand the result? Cool. Right, and so I guess you guys figured out the result, but this means that if SETH holds, then there's no 2 to the 0.99n time algorithm for any of these kinds of p's. So everything except what we really want, but it's a lower bound, so you know we have to accept what we can get, I think. So now I'm going to show you how to.
Is that the result? You don't have a result.
No, yeah, that's the end. I'm now going to show you the construction. Yeah. So how do we build these things? So remember, we want to build this interesting geometric object. We have this parallelepiped where all of the corners except for one lie on an LP ball.
are these objects studied?
As far as I know, they haven't been studied before.
They haven't been studied.
Yeah, I mean, although it's hard to check, right? I don't know what to Google. Like, we call these isolating parallelepipeds. So, you know, I asked a bunch of people and nobody knew of anything. That's the best I can give you. So let's just start filling in this matrix. And we're essentially going to fill it in with sort of everything that would be reasonable to put in there. So when in the k equals 2 case, we essentially just had 1, 1, 1, right? So all we cared about was, so remember, so y here corresponds to whether or not a literal is satisfied. And before we just cared about the total number of literals satisfied in the k equals 2 case. So y1 plus y2 plus y3. But you know, why not generalize? Why don't we consider other linear combinations like y1 plus y2 minus y3? And everything should be symmetric. There's no reason why we should care about the second literal more than the third literal. So we might as well do y1 minus y2 plus y3 and minus y1 plus y2 plus y3 as well. And we might as well give these some weights. So we'll multiply this by alpha 0, this by alpha 1. So it wouldn't make sense, again, to multiply this row, but to give this row a different weight than that row, because then I'd be saying that I care about the second literal more than the first, and morally that seems bad.
So you're simplifying your problem just by symmetrizing the weight.
Yeah, I'm remembering where the question came from, yeah. But also, I guess, I mean, this question is also symmetric in the coordinates, so yeah. I mean,
I assume the solution is symmetric, the center of the...
Well, I'm not sure if that's true or not, although I guess I know that solutions exist that are symmetric, so yeah. Yeah, I'm not sure if this is without loss of generality, but it works. For all but finitely many. So, and then let's just add in some other linear combinations so we can negate 2 variables now. And we can consider all negated variables as well. And we'll give these guys weights as well. So the guys with 2 negated variables are alpha 2. The one guy with 3 negated variables are alpha 3. So this is what I mean by we're just going to sort of solve this by brute force. We just sort of take the largest matrix that we could imagine being at all reasonable, and we throw some variables in and we try to solve it there. And so I need a t star as well, and so I'll just make t star. It's going to be some scalar. Each coordinate is going to be some scalar times these weights. And the reason I chose things like this is because, I mean, please don't actually read this formula, but what ends up happening is you get the distance for each assignment that I put in here, the distance is linear in the alpha I to the p, absolute value of alpha I to the p. Right, so you just get alpha 0 to the p, like, you know, the first coordinate is something times alpha 0 to the p, the second coordinate is alpha 1 to the p times something, third and fourth coordinates are the same thing, so you just get some linear expression in these variables. There are k plus 1 such variables. So since this distance is linear in alpha I to the p, it suffices, so we have this variable t star, and then we have this linear system that depends on t star, so it suffices to find a t star such that the resulting system of linear equations has a solution, with one caveat that it has to be non-negative because these are absolute values, so it wouldn't make sense to find a negative solution. So we have some matrix, M depends on t star, and we want, when we multiply it by the alpha zeros, this to equal, we want 1 plus epsilon up here and 1's down there. 1 plus epsilon corresponds to the unsatisfied assignment, and then we want all satisfied assignments to have distance 1. Cool? And because we chose our initial thing to be symmetric, our initial matrix to be symmetric, just by symmetry, although we prove it directly, you can see that if we set all the alphas to be the same, then all the distances will be the same. Essentially, if we treat every possible assignment in exactly the same way, then there can be no difference between the assignments, is what this says. And that's really, really nice, because it means that it suffices to find t star such that m of t star is non-singular. Right? So we had this issue that we needed positive solutions. But now I'm telling you, if I plug in some positive scalars for all the alpha 0 to the p, I'll get all 1's, and the system's linear. So now if I can find an inverse of just epsilon 0, 0, 0, 0, 0, and I scale it appropriately and subtract it from this, or add it to this, I guess, it will never make these guys 0. Cool? And the M-trees and MT star look like some hideous sort of pseudo-polynomials. So they're ugly summations that look something like this. But notice that for odd p, if I look in a fixed interval where all of these hideous absolute values take on some fixed value, they're either positive or negative, or they either add a plus sign or a minus sign, then I get a polynomial. So this is a piecewise polynomial expression in t star when p is an integer. And therefore the determinant is a piecewise polynomial in t star. Again, when p is an integer. And we simply need to show that's not always the 0 polynomial and p is odd. If it's not the 0 polynomial, then it has finitely many roots. So we can just check, you know, if it has, I don't know, p times k, I think, roots, then we can just check p times k plus 1 values, and we'll find one where we get a non-zero determinant. And then we're done. So it's like highly non-constructive. We give you a very simple algorithm for finding these things. It doesn't tell you much about what they look like.
Well, a random value would be good. A random t star would be good.
Yeah, with high probability, this is true. But I don't know what it looks like for a random t star either.
It's not totally non-constructive.
Yeah, okay.
A randomized algorithm.
But k is anyway a constant.
I see. Yeah.
No difference between.
Yeah, k and p we can think of as both constant. So I claim that they exist. Here's an example. This should be obvious. I assume if you just look at this, you all see that this is an isolating parallelepiped. Just use your intuition in 7 dimensions in the L3 norm. But I claim this actually is. In fact, it is. We solved one of these linear systems. So they do in fact exist. And this is essentially all I want to say. Now would be a good time for questions. Yeah.
Can you trade off the exactness in the... You want all the distances to be exactly the same except the distance to 0, which will be bigger. Suppose they were really, really close to being the same, and then it would maybe get there to 1.
Yeah, it's not possible.
It's not possible.
Yeah. I was very excited about that a couple months ago, but then one of my co-authors showed me an impossibility proof. Yeah. Yeah, we need arbitrarily close, and you can actually put a lower bound. Yeah.
What about like take several T stars that kind of all far from 0 but close to different points?
I don't understand the question.
Like if you don't try to do it once, like by one-time reduction, but to use the reduction several times with different T stars.
I don't think it helps. Yeah, I mean, maybe if I used like 2 to the n, so that I could like consider all possible assignments or something.
So I mean, it doesn't help for the construction, like.
Yeah, for the reduction, yeah. I don't think that generalization works. It's interesting because like before we had this reduction, we had something that kind of did something like that, but I don't think for this it helps very much, or at all. Yeah, because you can still, I mean, you know, like if I only try like polynomially many or even 2 to the little of n of them, I can still, there will always be some assignment that will fool me. There always could be some assignment that will fool me, and then it's useless.
Maybe not. Maybe you can somehow use them to cover. I'm not sure.
All right, yeah, I can think about it more, but I don't think it works.
So just to make sure I understand, so your reduction definitely doesn't directly work for L to the norm, but can you use sort of a L2 point something tiny to
No.
approximation or something?
Yeah, so first of all, this reduction, I'll show you something else in a second, but this reduction really relies on exact CVP, right? In fact, the instances it puts out, it creates are really obnoxious, right? Because I have this giant this giant identity matrix, this scaled up identity matrix at the bottom, and these 1/2s here. So basically, what I'm asking you to do, I'm giving you the integer lattice, and I'm giving you the all 1/2s point, and then I'm jiggling stuff just slightly, and I'm asking you what's the closest vector. So I really, really care about exactness a lot. So any approximation factor is gonna screw things up. As k goes to infinity, I believe the approximation factor goes to 1. And we do get like some approximation factor, but it's terrible. Yeah. But yeah, for all p, we get a reduction from constant factor approximate max 2 sat with n variables to constant factor approximate CVP with rank n. We're here. These are both constant factor approximations. So there's an analog of, and in order to do this, you just use the reduction I showed you before and just remove that identity matrix in the bottom. So as I was just telling Mark, the identity matrix at the bottom sort of makes this impossible, but it turns out that if you take it away, the reduction somehow still works. It's actually not that hard to see. And this particular implies under this assumption called Gap-ETH, which was introduced by Dainur, it shows that there's no 2 to the little of n time algorithm for approximating CVP up to some constant factor unless Gap-ETH is false. So Gap-ETH is the assumption that there's no 2 to the little of n time algorithm for approximating say max 3 sat. And it implies it for max 2 sat as well. One annoying thing is we're not sure if this reduction works for k greater than or equal to 3. I think if we had that, then we'd have very compelling reason to believe that 2 to the n is a nice lower bound even for constant factor approximation. And we even have like a reasonable conjecture about these isolating parallelepipeds, or I don't know if I'd call it a conjecture, a reasonable belief about these isolating parallelepipeds that if it were true would imply this. In addition, for all p, we show a reduction from max 2 sat with n variables to CVP with preprocessing with rank order n squared. So there's no 2 to the little of n, 2 to the little of square root n time algorithm for the CVP with preprocessing problem. If you don't know what that means, don't worry about it. But so those are other two results, and I'll now conclude unless there are additional questions. Cool. So this is just sort of our results summarized in table form. You can see for almost all p not equal to 2, we get this nice 2 to the n time lower bound, but the upper bound is not quite matching. It's n to the order n. We do get, so in parentheses here I have constant factor approximation, and under Gap-ETH we get tightness ignoring the constant in the exponent. And under this much less reasonable assumption, max 2 sat, we get this 2 to the omega n over 3 lower bound. In CVP2, we're sadly missing this spot right here. So things are much less well understood. I also get some results that I didn't mention, like CVP infinity, and also SVP infinity, which usually comes along for the ride when you get CVP. And actually, for these guys, even constant factor approximation is SETH hard, which is kind of surprising. And in upcoming work with Devesh Agarwal, we extend all of these results, except for the approximation factor. We extend these results to SVP for all LP norms greater than 2, with worse constants in the exponent. So the direction for future work is kind of obvious. We want to prove it for p equals 2. Maybe also we could think more about algorithms for p not equal to 2, now that we have a lower bound. And maybe we can solve, maybe we can settle the complexity of even SVP, though that's quite ambitious. And I think these isolating parallelepipeds are kind of fun objects, and maybe might be fun to think about them some more. So thanks.